Hey everyone, welcome to this explainer. Today, we're diving straight into the entity relationship model and honestly, looking at exactly why it is the absolute blueprint for modern data architecture. As technical data professionals, you already know the deal. Managing raw data without a solid blueprint, yeah, that's a total recipe for disaster. So, we're going to explore how proper data modeling actually transforms fragmented, chaotic information into a highly scalable, unified asset for the entire enterprise. Let's get right into it. Here's our system schema, the agenda for today. 1. The grammar of data. 2. Anatomy of the ER model. 3. The three modeling phases. 4. Normalization and constraints. 5. ER versus other data models. And finally, 6. Why data modeling matters. All right, starting off with Section 1, the grammar of data, synthesizing the chaos. So I have to ask, why do data projects actually fail? Well, you know as well as I do, it's almost never the compute engine failing us. Very often, it's simply because teams skip that crucial initial modeling phase. And when that happens, boom, you get shadow IT, you end up with these walled-off pipelines where one team's hard-coded definition of a customer completely collides with another's. The next thing you know, a silent schema drift triggers massive downstream dashboard failures, and all that hard-earned business trust, it just completely evaporates, gone. Moving on to Section 2, Anatomy of the ER model, the core building blocks. First up, the entity. Now, instead of just viewing these as the basic nouns of the business, I want you to think of entities as your primary business domains: a customer, an order, a product. In physical relational systems, these dictate your core table structures, and they literally form the backbone of your transactional integrity. These are absolutely the primary domains you have to govern. Next, we have attributes. Attributes give our entities actual substance. For us as technical architects, attributes aren't just minor details, right? They dictate the precise scalar data types, the nullability rules, and the exact memory footprint we need to capture. So for a customer entity, this dictates exactly how we structure and validate things like strings or integers for names, emails, and phone numbers, all neatly inside our column constraints. And finally, relationships. This is really where the logical network takes shape. Relationships define the operational constraints between our domains. Usually visualized with that classic crow's foot notation, these paths dictate exactly how we're eventually going to write our join clauses and how we'll enforce referential integrity across the entire system. It's how the whole puzzle fits together. Let's move right along to Section 3, the three modeling phases, abstract semantics to physical reality. Just like constructing a massive skyscraper, we have to progress step by step through layers of abstraction. Phase 1 is the conceptual model, Phase 2 is the logical model, and Phase 3 is the physical model. Seriously, skipping directly to the physical build is exactly what causes those bottlenecks and massive structural tech debt we were just talking about. There's a really stark contrast here. The conceptual model is entirely platform agnostic. Actually, scratch that. It's more than just agnostic. It's completely business-oriented, and its main job is forcing the enterprise to finally resolve those hidden disagreements about domain definitions. Conversely, the physical model is where you actually commit to engine-specific execution. This is where you're making the hard calls, like deciding on JSON-B types for Postgres or optimizing micropartitions for Snowflake. And sitting right there in the middle is the logical model, perfectly translating those business concepts into a structured, normalized blueprint, completely free from the constraints of any specific database software. All right, Section 4, Normalization and Constraints, Enforcing the Rules. So, keys and cardinality map out the exact permissible boundaries of your system. Primary keys enforce your entity integrity, which often requires us to make tough architecture decisions, like choosing between natural keys or highly scalable surrogate keys. Then, foreign keys step in to establish the referential links, and resolving cardinality, especially identifying and decomposing those tricky many-to-many relationships into associative bridge tables. That is an absolutely critical step before you even think about generating a physical schema. One-to-one, one-to-many, many-to-many, they all have to be strictly defined. Now, to keep our data pristine, operational databases almost always target third normal form, or 3NF. The rule is simple. Every non-key attribute must depend only on the primary key. Look, if you've ever had to update a customer's address in 5 different tables and somehow triggered a massive deadlock contention nightmare in production, well, then you know exactly why eliminating redundancy through 3NF is absolutely mandatory for transactional systems. Let's pan out a bit for Section 5, ER versus other data models, navigating the ecosystem.
While highly normalized relational models are absolutely perfect for ACID-compliant daily transactions, they can cause massive compute overhead when you start running complex analytical queries. That's exactly why data warehouses often pivot to dimensional modeling, like Kimball's star schema, where we deliberately denormalize data into fact and dimension tables for lightning-fast aggregations. Alternatively, if you're dealing with massive scale and need strict historical auditability, enterprises often adopt Data Vault 2.0 architectures, cleverly organizing data into hubs, links, and satellites. It's all about picking the right tool for the job.
And we definitely can't ignore graph modeling. Instead of your traditional tables and foreign keys, graph databases like Neo4j use nodes and edges. Here, relationships are elevated to first-class citizens. This totally eliminates those incredibly expensive multi-table joins when you're querying highly interconnected networks. Think complex fraud detection rings or intricate recommendation engines. It's a real game changer for that specific kind of data.
Bringing it all home with Section 6, Why Data Modeling Matters, the Foundation of Trust.
Ultimately, a rigorous modeling process is exactly what transforms a data liability into a highly scalable asset. It creates a governed, single source of truth. It completely eliminates that dreaded shadow IT, and it radically accelerates your pipeline from raw ingestion all the way to actionable business insights. Most importantly, it ensures strict data governance, making it explicitly clear exactly who owns the data and how it is protected. I love this quote. AI readiness starts with data. Why data modeling is the foundation for enterprise AI. It really hits the nail on the head. You literally cannot feed an AI agent a swamp of undocumented, redundant tables and expect intelligent outputs. It just doesn't work. Advanced machine learning and enterprise AI depend entirely on the deterministic, well-structured data flows that only proper foundational modeling can provide.
So, I'm going to leave you with this to chew on as you design your next pipeline. Is your underlying data architecture structurally sound enough to support the future of your business? Investing the time in a rigorous entity relationship model today will undoubtedly save your engineering team from endless downstream headaches tomorrow. Thanks so much for joining me on this explainer, and happy modeling.